or you could run the JIT in parallel, although we have evidence that that's not what's happening here. That you're actually getting better code faster would be one thing you could do with these extra processors. That's not happening in this data. We did the details on that. But if you, like, it doesn't help you to go to 4, although it did help you a little bit to go sorry, it doesn't help you to go to 4x2 because of the problems with the SMT, but you do get some reasonable weak scaling on single-threaded benchmarks on a Java virtual machine. There's no scaling at all on the C sequential benchmarks, just as you would have been doing, all right? So I'm not going to show you that data, it's boring, all right? Giannis.
But even that, we knew that would have been just a constant improvement, right? We knew that from the VM parallelism we would get at most a factor of 4. Mostly it's the DC that runs in parallel, right? So
right, but
it wouldn't help the virtuous cycle in the long term. It would never help to give us exponential improvements.
Well, we're not going to get exponential improvements because we're not increasing the core count in an exponential fashion. If the software is perfectly parallel, we still can't exponentially add CPUs onto our die like we could transistors for technology reasons that I won't go into, right? But we should be able, why are we getting 2.5, right? Is the VM sucking up that much time? You would never think that this is like a fairly real benchmark too, Antler, right? In this particular case, the GC is working much better on Antler, and it was a disproportionate amount of time. But you shouldn't have been able to get improvement anything more than 2, right, on any benchmark. I was surprised. David.
So reassure me that this JVM, I don't know anything about it, doesn't just happen to use the world's worst GC algorithm.
David, you do know everything about this is hotspot. This is your baby.
I didn't say. I didn't know.
This is hotspot. Sorry, like to try to get through this.
It doesn't use my collector anymore.
It should. Huh?
But is this a good collector anyway?
This is the production hotspot configured as best you can, with some warm-up time so we're not just measuring the first iteration.
Generational?
Yeah, yeah. This is a, we tried to be very nice to the hotspot VM since people will always ask us about that, right?
Maybe,
all right.
Maybe Sun was trying to sell multiprocessors.
I would have bought them. All right, so let's look at the multi-threaded Java. So that was good news, right? Do we have more good news? Do we have good news, better news, or worse news? What should we have? We should have better news. Do you think we have better news?
Yeah.
We don't, unfortunately. All right, so we have, if you look back at this number where I said I would have expected nobody to be over 2. Now we have 4 of our parallel workloads over 2. So that's not enough. All right, with 4 processors. So we're getting some scaling, but we're also slowing some programs down, unfortunately, by using parallelism. All right?
Gosh, we never saw that. Oh, you heard that.
I don't believe you. All right. And this is Sunflow. Sunflow is a pretty parallel workload. It's a graphics workload. Yes, we slow down Sunflow when we give it more processors. All right?
Is this just a proof point for what kind of Cliff said, is you give these people locks and they just put synchronize everywhere and that's what happens?
You know, so I agree. There's
some poorly written programs.
There are poorly written programs out there. There's poorly written programs because we don't have the right parallelism constructs yet, like what they are and how to program them. All we have are low-level constructs like lock and unlock. That's not good enough, right? Are these programs correct? I don't know. Do they have races? They could. We don't know that for sure, right? And but the geo mean is not happy, right? And SMT is a little more useful in this circumstance. You do have some synergistic threads that get to share, but not as much as you want either. All right? So one last So we're not where we need to be. It could be because the applications don't scale. Could be because the VM's getting in the way. We don't know the answer to that yet. All right, but this is kind of where we are. All right, and then one more slice of our really interesting data. Okay, so all the performance we are getting is coming at a disproportionate cost in power. All right, and that's not going to help us in the long run either, as power becomes the dominating concern. So the highlighted, circled are these. I've got the native benchmarks now over here, and I've got the Java benchmarks over here. Okay, so the native benchmarks, and I want to draw your attention to this dot and this dot. So that's the i7 on 45 nanometer technology, and this is the hollow. All the hollow benchmarks, all the hollow symbols are sequential programs. All right. And all the solid symbols are programs that are supposed to have concurrency. All right? And so this is an imperfect comparison because the parsec benchmarks that we're using for our native multi-threaded benchmarks are more kernel applications. So they don't trash the instruction cache. They're very tight. They've been coded by a bunch of people who want parallel algorithms to work and want to sell Intel machines, and so all these algorithms scale really well. Okay, and the Java benchmarks are just big hairy benchmarks that happen to have concurrency in them that may or may not have been optimized by parallelism experts to get that kind of performance improvement. All right, so if you look at these two dots, when you're getting good performance improvements, you're paying some in power. You've gone from 40 to almost 100 watts, right? But here, and the 1 watt, and this is a log scale of measured average power, the 1 watt is about what the Atom 45 takes, the Atom in 45 nanometer technology takes. But you're getting good performance for that, okay? So you're burning more power, but you've got a factor of 6 performance. All right. Over here, we're going up, and we're not getting the same. We're not getting the same in the concurrency, and we're paying just as much power. All right, or not quite as much power, but we're paying a disproportionate amount of power. Phil.
Well, but that includes the multi-threaded benchmarks that didn't scale, right?
That includes, yeah.
But wouldn't it be more useful here to make a cut between the benchmarks that just happen to be concurrent, which are guaranteed to perform worse on a multi-threaded on a multiprocessor, versus benchmarks that are multi-threaded in order to get parallelism, which are guaranteed to perform better, right? I think there's sort of a distinction.
Yes, you can't divide up this data better, right? But I feel like it is useful to show, like, if you know what you're doing, you can get these machines to scale, but you have to pay for a lot of that. There's a lot of power to be paid for that.
I guess I'm curious how much, because this is interesting, right? You're showing the power performance trade-off. I would be really interested to see the power performance trade-off for those multi-threaded Java programs which were designed to scale.
Well, you could argue that why are they multi-threaded if they aren't designed to scale?
Because threading is not for parallelism, it's for concurrency, which is different. It's for responsiveness.
I don't know the motive. It's true, but I don't know the motivation for each of the applications that we have. Whereas I do know the motivation for all the parsec benchmarks because of who distributed them and what they wrote about them.
This is an easy question. You said that graph shows that the power is going up disproportionately. Could you just point my eyeball to 2 points I should look at to see that?
So this, because it's on a log scale, we're going over two lines for the performance.
So performance is scaling about twice, right?
Right.
There?
No, we've gone a log scale.
From 6
so
to 12?
12, so we got about twice, and here we got about 2.5, right? Because we went from 40 to 100.
So it's not going up by too much more than
more,
performance.
but it's going up more, right?
But right. So I squared R losses maybe or something like that. But it's not, I guess what I'm saying is, it doesn't look
It's
wackily
not-
out of proportion to me,
it's
just a
not-
little bit out of proportion.
That's right.
Okay.
Just like the power wall is just a little bit scary, right? We're only consuming 1 to 5% of all the world's power by running data centers right now.
I thought maybe there was.
I mean, I do think, like, it's starting to matter. Every little bit is starting to matter.
I'm
right?
looking on the right too, and it doesn't look wackily out of proportion there either, but maybe I'm misreading your graph.
Well, here we're not getting any performance, really.
Well, it's going from what, 6 to 7 -ish?
6 to like a little under 7,
Yeah, and it's
So,
going up from
a little bit.
25 to 30 maybe. That doesn't look too bad.
Not too bad.
And then the other one is going from, you got circles going from 40 to, is it 60 I'm reading on the power?
Right.
And then it's going from about 6 to 7, 8 on the performance. So that one's a bit, that one maybe is a bit worse. It's a little hard to tell on the log
Right.
scale looking at the slope, that's all.
It's not perfect.
I'm trying to do numbers in my head. Thanks, Kathryn.
All right.